Okay, so our first speaker is Sven Bachmann from UBC, and he'll be talking about Abelian Anyons and gap quantum lattice systems.
All right, thank you very much. Thanks. I want to thank the organizers for inviting me. I was there yesterday and realized that I'm a little bit of an exotic person in this community, but I'm very happy to have the chance to speak here and maybe get some feedback. So what I want to present here is joint work with Alex Bolz, who's in Denmark, Wojciech de Hoek in Belgium, and Martin Fraas at Virginia Tech. And I want to talk about, how, here's my title, Abelian Anyons and gapped quantum lattice systems. And so here's the plan. I will actually first explain somewhat precisely what I mean by the words in the title. So I'll describe what I think, how I think of anyons, what I exactly mean by gap lattice systems, and then I will actually describe the type of things that I want the type of systems I want to analyze, namely systems that have U1 charge, and I'll explain how you can construct quite generally Wilson loops in them, and out of that I will see that naturally anyons arise very generically in these very natural systems. And if I have a little bit of time at the end, I would like to, after I've described this anyonic part, try to briefly mention that this is related to another problem, which is the problem of charge transport in quantum systems and the relation to the quantum Hall effect. So, here's how I think about at least Abelian anyons. And let me immediately say that this is not, for me, this is really dates back to the original paper about that by Lienas and Miheim. So, here I have, let me use the little pointer if I can put it somewhere else. Yeah, so I am on a manifold. Think of Rn or maybe a torus. I will actually use the tori later. And I have point particles whose positions are xi and xj. And so the configuration space is, you would a priori say, well, it's the n, if you have n particles, it's the n-fold product of the manifold, but not quite, right? Because these particles cannot sit on top of each other. So that's why you have a constraint, right? So that xi is not equal to xj, right? And so even if m, if my manifold is Rn, because you have this constraint here, you may have, in particular in low dimensions, you will have possibly a non-trivial topology of the space of configurations. Think of the configuration space in one dimension, right? And two particles. Then this is a line, right? This is the diagonal line, and you see that this space is not even connected in this situation. Okay, so this constraint that you have point particles not being able to sit on top of each other yields a non-trivial topology of this configuration space. Okay, so that's a configuration space. Whether this is classical or quantum mechanical, this is of course exactly it's always like that. So now we are in quantum mechanics. So I want to describe a state. In fact, here in this case, I will only talk about pure states. So state, you like to think of it as a square integral function on this configuration space, so this psi. But as we all know, really, it's not really the vector, but the one-dimensional projector, which is the space. So that's the corresponding projector. Right? You could write this as Brian Kett, if you want. So the p psi is the one-dimensional projector onto that pure state psi. And if you write it this way, it's pretty clear that the phase of the vector does not matter, right? So you change the phase of the vector psi, you get exactly the same state, right? This is a fundamental thing in quantum mechanics. Now you see when you talk about anyons, so let me move this up here so that we can all read the bottom of my slide. So you always think of this idea that you're moving particles around, right? So what does that mean? What does moving particles in this setting mean? It just means you pick a path. You pick a path here, denote, this is not what I want to do, like this. So you pick a path, so it's just a map it's a path in configuration space, right? So gamma S is just it's just, if you want, it's represented here by these arrows, right? So continuous path, these particles are moving in configuration space. Accordingly, the state is changing, and I will denote. So you get a path within these family of states, right? Which is P of S. Okay. So far, I hope so far so good, right? So I get this picture, and you see there's a natural, immediately some geometric picture arises. Why can I not go to the next slide? There it is. Right. So and when you talk about anyons, then you usually talk about closed paths, so loops in configuration space. What is a loop? So you remember gamma sub S is denotes this path as a function of S. Think of S running between 0 and 1, right? So a loop is just that the final point is equal to the initial point. So gamma at S equals 0 is equal to gamma at S equals 1. So that is a loop in configuration space. So again, what does that mean at the level of states? Well, it means that the projector at the final, at the initial time, if you want, S is equal to the projector at the final time, S equals 1. So the projectors are the same because you're coming back to the, to your initial position. But of course, and again, this is not new, I suppose, but the vectors, even if you change, these vectors continuously along the path, well, you may come back to a state. So the state psi1, as a vector now in the Hilbert space, may differ from the initial state psi0 by a phase, right? And that phase depends on the closed path you've taken, right? It turns out that this phase, in fact, depends only on the homotopy class of the path. So you can deform the path a little bit. As long as you stay in the same homotopy class, you will get the same phase. And if all of this is a little bit abstract, in fact, it all works in particular well in 2 dimensions. So I've plotted here a 2-dimensional sketch. So here's you have, there's lots of particles, these dots, but I just look at 2 of them, xi and xj, and I think of my path of configurations to be such that only one particle moves around. It's the particle xi, and it moves around, just goes around another one, xj, right? So if I plot this loop here, somehow in time, I think of S as really being the time parameter here, going up, from bottom to top. And I have my particles xi here and xj there. So xj doesn't move, so its world line just goes up, straight up. But xi moves around, and it moves around xj, which does exactly this, right? So now you see, in that particular setting, you immediately see that this whole picture of moving particles around in configuration space naturally comes, the natural objects that come out of these are these braids, and therefore you see that the braid group comes into the game. And why is this useful? Well, you see, so for each loop, now I get back to my original equation, which was for any loop, right? You see that for each loop, you get a phase here, right? So in fact, what you see, what are these phases? Well, they represent, if they are a 1-dimensional representation of this group of braids, this group of loops, okay? So that's exactly how people, think. Why do I have trouble? So how people think of loops and anyons. This is how I would like to have, that's what I would like to have in mind. So really, this whole picture that I developed in quantum mechanics, right? This is really a quantum mechanical picture. It shows that if you have these particles that cannot sit on top of each other, then you necessarily have a representation of this fundamental group, right? The fundamental group here of gamma n is the configuration space, right? And it's given by this phase that you pick as you go along a loop, right? Again, here I've presented this as so pi1 of gamma in this fundamental group. Well, you can think of it as a fundamental group, and people would also call that the colored braid group. Why colored? Well, because you see here, I thought of these particles as being distinguishable. This won't play much of a role in this talk. If you could also do the same with indistinguishable particles, in which case, exchanging two particles is also a loop, right? But we won't talk about this. And so we speak of anyons. What are anyons? Well, anyons are just particles that carry a non-trivial representation of that group. So first of all, you need to have that the fundamental group here is non-trivial itself. So that depends on the topology of the manifold, right? And well, not only is this non-trivial, but the representation itself is non-trivial, right? So that means sometimes if you move particles around, typically one particle around another one, you get back to a state where the phase, you've picked up a non-trivial phase, okay? So that is very analogous to parallel transport. If you think of moving a vector on the two sphere, right, in a parallel way, you go along a loop, you come back to not exactly yourself, right? So there's a whole geometric picture behind this, which is very natural. Again, all of this has been, understood long ago. So the possibility of the existence of such particles is really due to these two authors, and shortly after, so that was in the 70s, right, where people realized, well, in 2 dimensions in particular, this fundamental group here tends to be non-trivial, and therefore I may have non-trivial anyons, right? Then, around the same time, people said, hi, look, there are physical systems where we can believe that such particles arise as the fundamental excitations, and this was in the quantum Hall effect. This is the famous Laughlin wave function, where you can actually show that quasi excitations carry or are anyons. And more recently, this has become again very trendy. This is now closer to this community because people have constructed very explicit models. There's the quantum double model of Kitaev, there's these Levin-Wen models, and others that we've heard about yesterday, where these anyons arise very explicitly. But I would argue that these models, in particular here, are very much constructed for that goal, right? They're not, in a sense, very physical models. They start from some abstract group and so on. So and you can see these anyons arising, but they're very tailor-made, so to say, to see these anyons. And what I would like to argue today is that you don't need this very specific details of a model to see anyons arising, and that in fact anyons, at least in 2 dimensions, are completely general properties, at least provided you have a spectral gap. Okay, good. So let's so that's I talked about anyons. Let me briefly also say what I mean by a quantum lattice system. So for me, these will be I'll work in finite arbitrary large but finite volume.
Can I just ask a question? Can I just interrupt you?
Of course, of course.
You said you're dealing with 3 dimensions. So are you envisioning your anyons somehow as line-like objects?
Did I say
all
3?
your braids?
Did I say 3? I meant 2.
Okay, maybe I misheard you. Okay, 2 dimensions. Good then. Yeah.
No. So precisely in 3 dimensions, you can prove that the braid group has only representations that are the same as the permutation group. So this really is interesting in 2 dimensions, right? And I will talk really. We should all have in mind that I'm either on the plane or on the 2-dimensional torus. Okay, and precisely. So on this, let's think of the torus. On the torus, so the setting is like this: that you have a graph. I'll sometimes speak of a lattice, but it doesn't need to be regular. You have sides on each side. You have there's 2 things: either the thing of a quantum spin system, where at each side you would have a spin, or you think of lattice fermions, where you have fermions that can jump between these different sites. Right here, I've described the setting for fermions, but again, everything I will say later also works for quantum spin systems. Okay, so for fermions, the observables are given by essentially polynomials in the creation and annihilation operators at each site. So these are these A's. And the important thing that will play an important role later which is particularly easy to explain in this fermionic setting, is that you have a charge operator. So the charge operator is here, right? So for fermions, what is the charge? Well, it's also the number operator. So at each site, you can ask how many fermions you have. As we know, they can be only 0 and 1. And you see here, I have a specific natural charge operator, but really the only thing that I will use later is that I have a charge operator whose spectrum is in the integers. For the fermions, it's only 0 and 1, but in general, you could have something else. You would have various types of fermions. And well, charges at different sites commute with each other. Okay, so that is really an important part of the setting, that I have such a charge operator with integer spectrum. And of course, if you take a finite subset Z like this, well, you can naturally define the total charge, which is the sum of the charge operators contained in that set. Okay, so as I said, I speak of fermions, but you can just as well think that at each site there's a quantum spin. So you see, I will be now telling you, here's a general family of Hamiltonian, right? And give you really what I need, what kind of assumptions I need for my Hamiltonian. So I think of a family of, I think of Hamiltonians as being like this. So they're just a sum of interaction terms. These 5x, for me, these are the interaction terms that act within the set X. So X is finite subset of my lattice, a number of sites, right? And 5x is all interactions within these sites. I will think of finite range interactions, namely these interactions. There's no interaction as long as the distance, the maximal distance within the set X is larger than some range R. Okay, so that's what I mean by a local Hamiltonian. It's just a sum of finite range interactions. And importantly, so that's in my initial slide, I said there's a U1 symmetry. Well, that's because there's charge conservation, if you want, or U1 symmetry, depends how you want to call it. But each of these interaction terms commutes with the total charge. So Q lambda is a total charge operator, and the interaction here commutes with the charge, right? So this is this U1 symmetry. And if you don't like this kind of abstract setting, you can think, here's a concrete example of a Hamiltonian that satisfies these conditions. You see, you have some hopping here with some hopping amplitude. There's a density interaction here, if you want a charge interaction. So you see, this is quadratic in the A's, this would be quartic in the A's, so there's some true interaction, and maybe there's also an interaction with an external potential. That's, again, I'm not saying that what I'm saying is restricted to this, but this is just to have a concrete things in mind. Again, you can think also of a spin system like toric code or perturbations of toric code, things like that. Or Heisenberg model, that would all work. Okay. Okay, so that's the kind of systems I have. There's this charge, there's this charge operator, and as I said, so the only real assumption that I will need to make to be able to see how anyons arise. So you see, so far there's no anyons, right? There's just fermions. I've just started with fermions. They have a normal unit charge, so there's nothing special so far about this system. But I will need to assume two things. I will assume that there's a spectral gap. So E0 is the ground state energy, and I assume that there's, the first excited energy, right? E1 is separated from the ground state energy uniformly in the volume. Okay, and this is really the important. This is where in finite volume, all of this is really a finite dimensional Hilbert space. So it's a finite matrix. Of course, in any finite matrix, there's a gap between the lowest eigenvalue and the first eigenvalue. But I will assume here that this gap is there uniformly in the size of the system. Okay, and that is of course a very strong assumption that is in general hard to prove. But we know some models where this is doable. For example, the Hofstadter model of quantum Hall again. And you assume also that the rank of the ground state, so P is the ground state projection and will be the ground state projection for the whole talk, that this has finite rank, little p. And again, this is uniform. So you don't have a ground state degeneracy that increases with the volume, but it's finite and doesn't change with the volume. Again, think of toric code or any quantum double models. They have this property. They're gapped and they have a finite dimensional ground state projection. Okay, so if you have that, of course, we all know this, that because the Hamiltonian commutes with the charge, that's the U1 symmetry, then the charge also leaves the ground state space invariant, right? By this I mean that Q acting on the ground state space, is still an element in the ground state space, right? So, or you could also put this as Q commutes with the ground state projection. Okay, so the ground state space is invariant. It has a well-defined charge in it, right? That's the charge on the full system. Let's say on the torus, it's the charge on the full system. But of course, if you take a finite system, you take a finite subset, finite number of spins, if you want, or finite subset in your lattice, then, and you look at the charge in that finite set, then of course, this will not be true anymore, right? The charge in a finite set is not necessarily, is not a good quantum number if you want. So there's fluctuations of the number of charges in that set, right? And these fluctuations, where do they appear? Well, essentially at the boundary of my set, okay? So the point is, I do not have this kind of conditions for any other set than the full lattice, right? Still, and this is my first little point. In fact, here's what you can do. So you pick a finite set Z here in my lattice, right? So you can look at the charge in that set Z. This is this QZ, and it turns out that you can construct very explicitly. You can construct an operator which I call KDZ here. That's an operator that really lives only on the boundary of the set Z, right? So such that if you add it or you subtract it to the charge, then in fact you get something which is, which commutes with P, which leaves the range of P, the ground state space, invariant, right? So by modifying the charge operator at the edge, at the edge of that domain Z, and this holds for any Z, right? You can actually make the ground state again invariant under the action of that modified charge operator. Okay. Again, I explained, what does it mean to be supported in a set? That's just that you can write, so this KZ can be written in creation and annihilation operators only, for the sides along that boundary. And really, around I mean, by this, I just means that it's not exactly this. It's not exactly supported on DZ, but it's supported on this boundary up to tails that decay very fast in the distance away from the boundary. Okay, so that's the point. So if you have a charge in a finite set, you can modify it at the edge, to make that new modified charge operator leave the ground state space invariant. Okay, so let me go a little bit into this. I think the construction is very simple, but it's at the same time it needs a little bit of technical construction. So this is a construction that we've learned from Hastings, really, but applied in a slightly different perspective than when he introduced the quasi-adiabatic evolution. So here's the construction where you take any observable. So this is a polynomial in the creation and annihilation operators. And what do you do? Look, let's directly go to this one. You evolve it in time with the Hamiltonian. Right, I have a Hamiltonian, so I can evolve the observable in time. And then I just integrate the result, against this weight function W. And this weight function, it has really two important properties. The first one is it decays very fast in T. So for all practical purposes, you can think of W as a function of T as essentially being a cutoff function, so that this, it essentially cuts this integral here to a finite interval, essentially, right? There's again some tails, but that's the moral of the story. On the other hand, it has a good Fourier transform, and the Fourier transform is like this. So here's, so W hat is the Fourier transform, and W is exactly one of a K, one of Xi, right? The Fourier transform of W is exactly one of Xi, not for all arguments, but at least whenever the modulus of Xi is larger than the gap. So G is the gap of the Hamiltonian. Here's the Hamiltonian. It has a gap G. And W, as long as, you know, the modulus of Xi is larger than G, it's exactly 1 over Xi. You can construct such functions. You know, there's an explicit function that satisfies this property. And so here's the point now. Okay, you look at this, and you think that my observable O here has only matrix elements. You know, you go into the eigenbasis of the Hamiltonian, and you assume for now that this observable has only matrix elements that link, you know, states within the gap, you know, states in the ground state space and outside of the ground state space, but only like this. So it's only off diagonal with respect to this ground state projection, right? So you see, if I have a projection, I can of course always write any observable like this as a block matrix. This is whatever happens in the ground state space on the off diagonals, you know, away from the ground state space, and these are the diagonal. So suppose for now that O only has, you know, off diagonal contributions. Why not? Well, then you see, in fact, here you only see differences in energy that are larger than the gap, really. But there, you know, that W is exactly 1 over, you know, 1 over Xi, which means, in fact, that this whole thing there is really just a way to write the inverse of taking the commutator with the Hamiltonian, right? So here's the formula, right? For those off diagonal operators, this whole map applied to the commutator of O and H, you know, you do nothing. So O is exactly I of this commutator. Again, think of this as taking this integral here inverses the operation of taking the commutator with the Hamiltonian. Again, that is something that really goes back to Hastings if you think about it. Okay, so why is this an interesting thing? Well, because in fact it allows me to basically diagonalize or block diagonalize operators. So you see, if I now take any operator, not necessarily an off-diagonal one, and I define this A bar, which is A minus this thing that I've just seen before, well, you know, what do you do? You exactly take the off-diagonal part, right? So you take the operator, and you take its off-diagonal part, which means then the only things that are left are the diagonal elements, you know, the block diagonal elements of A. Another way of putting this is A bar commutes with the ground state projection. Okay, so for any observable, I can modify it like this to make it commute with the ground state projection. And again, this is because I've assumed that the Hamiltonian has a spectral gap. So that's in a sense the spectral property of this map. It has also nice locality properties. You see, because if I look at I have O, I have a time evolution here. So that time evolution, you know, you may know the Lieb-Robinson bound. Otherwise, I'll just say that the support of O only grows linearly in time. And if W is essentially a cutoff function in time, then if O was localized somewhere, then I of O is essentially localized at the same spot. So that's what I write here. Why do I have a B there? This is supposed to be an O. So, you know, the support here of O, if the support of O is some subset X, then the support of I of O is essentially, again, the subset X, up to tails again.
Sven, there's a question on the Q&A. Can you see it? Or?
Yes, can I,
yeah,
yes.
You can see it.
2 small questions, so I'll read that, or does everybody see that actually?
No, you should better read it.
So 2 small questions. 1, the ground state projectors and models. Can they include models with degenerate ground states, where I can take stakes characterized by P as superposition of ground state sectors? So yes, absolutely. This is important. As I wrote, the rank of the ground state projection is little p, and little p does not need to be 1. So yes, and in fact, this will play an important role. I will see anyons only if this ground state projection is, the ground state energy is degenerate. And second question is, can I think of the W operator as a retarded fermion Green's function? Can you think? No, not really. I wouldn't say that actually. No, you should really think of this as just a little bit of a smeared time evolution. So it's really a time evolution, but a bit of an average time evolution. that's how you should think of this I, this I operator here, right? W here is just a function, right? It's just a function. And so here, it's a filter. I think if you go back to Hastings, he calls that a filter function, right? It's that's what it is. Okay. So I can diagonalize that kind of operator. So let's now go back to the charge, right? I have charge conservation. So because of charge conservation, if I have the charge here in a finite set, right? This is just the charge in that finite set. Well, you see, HQ is the change of the charge. If you want, this is the current, right? Up to an I, maybe little I. So this is essentially the current. If you have charge conservation, the current, the change of charge is really localized only at the boundary, right? You could also see, I told you what I meant exactly by charge conservation. This is also an algebraic identity, but this is also very physical. This is really just a continuity equation, if you want. The change of charge is at the boundary of Q. Okay, so if I apply my supermap I here to this commutator, well, because this commutator is on dz, this is also supported essentially on the boundary dz. And I've just said that, in fact, for any observable, the Q bar, which is defined by this, leaves the ground state space invariant. And this is exactly what I wanted to do. I modified Q by this K to get an observable, an operator Q bar, which leaves the ground state space invariant. And the modification here leaves only at the boundary. Right, so this is it. I can make P an invariant space for Q bar. So that's a little, that's in fact, it turns out to be a useful little trick for many things. So this kind of block diagonalization that I can do here using this function W. But so let's go now towards one specific goal, maybe understanding anyons. And so here it is. Let me take here an exponential of this Q bar. Why not, right? It's important that I take this exponential at 2 pi. So you see, Q bar, it's this difference between Q and K. Q is a sum of local terms, right? It's the sum of charge at every single site. So what I can do is I can decompose Q as the part that lives on the boundary, and the rest. The rest is, well, the total minus the boundary. Right, so eat the Q bar. You see, I have here the boundary part and here the bulk, if you want, in the inside of Z. But you remember now I have a U1 charge. Having U1 charge means Q has integer spectrum, right? So if I take e to the 2 pi I, an operator which has integer spectrum, right? But if you can think of diagonalizing it, you have all these integers. You have e to the 2 pi I the integers. That gives you the identity. So in fact, this operator here is just the identity. So you see, the bulk part completely disappears, and I'm left with this exponential, which only lives at the boundary. Okay, so out of my Q bar, by taking the exponential at 2 pi, I get an operator which is really a loop operator. And I think in this community, you guys all like loop operators, so I can construct out of any U1 charge here, I can construct one of these loop operators. So I like them. I will call them Wilson loops because they're loop operators and they leave the ground state space invariant. They act on the ground state space, right? But they leave that ground state space invariant. Okay. So I can construct them, and again, so this is a very general construction. I didn't need anything. I just needed a spectral gap and a U1 symmetry. That's all I needed to have to get this. Now I'm getting to something, to really the point. So I write, like as I just, that's not what I wanted to do. So here it is. So I have this ground state, this exponential leaves the ground state space in there. And this is these loop operators. But so far I've done that, for, I didn't specify the set Z. So now let me be specific. So I think that really I'm on a torus. Now I'm on the 2 torus. And I take for Q the charge, right? Really the charge in this half torus, right? Okay. So what I said before applies here for Z being, this half torus gamma. So I can construct my v, which is the exponential at 2 pi of my changed q bar. Again, you know, this q bar here in the bulk of gamma, it disappears. So I only have two contributions, one which is associated to the del minus and one to del plus here. So these are these two terms, which I will call v minus and v plus. So see, these are again loop operators, right? V minus is an operator associated to that loop, v plus an operator associated to that loop. Okay, and you can convince yourself, this is really by clustering or by exponential decay of correlations, that again, both of these v plus and minus again leave the ground state space invariant. This is a consequence of the fact that v itself leaves the ground state space invariant. Now, you see, and here's in the sense why this becomes interesting. Now these v's are exponentials of something, except this q bar minus, which is just the, you know, the part of q bar which lives around here. Those guys do not leave p invariant in general. Their exponential does, but not the q bar minus themselves. Okay, and so I have constructed these loop operators, these v minus here, that are, you know, leave p invariant. But you see, now why is it important that I'm on the torus? Because these loops d minus and d plus, they are loops, but they're not, you know, this is really in algebraic topological terms, they're not boundaries, right? They're non-contractible loops if you think in homotopy, right? So d minus and d plus together form the boundary of gamma, but d minus alone is not the boundary of any set on the torus. Okay, so what is special about these? Well, you see, so let us, you know, I'll finally do the last big assumption that I want to make on these models, which is topological order. There's various ways of talking about topological order, but you know, what do you want to? How do I want to think of topological order? That local observables cannot, you know, are trivial on the ground state space. Now these Qs, these QZs, they're sums of local observables. So I assume that these QZs and the corresponding Q bars that are all sums of local observables leave the ground state space. You know, they do not necessarily leave the ground state space invariant. That's not the important part, at least. But when I look at them on the ground state space, they're, you know, they're just the identity. They don't mix the various ground states with each other. Right, that's really what this equation means here. Q is some number on the ground state space, but you cannot with Q move between the various ground states. Good. So what have I seen so far? Well, if you take a loop on my torus, which is a contractible loop, if you want, or the boundary of a set. So alpha, this loop alpha is the boundary of something dz. Then in fact, and this is exactly what I was just talking about, my V leaves the ground state space invariant, and because it is the exponential of something trivial, it is trivial itself. So these Wilson loops are, the Wilson loops associated to boundaries are trivial on the ground state space. They don't do anything. However, none of this holds if the loop itself is not a boundary. So it's typically one of these non-contractible loops on the torus. So in that case, V acts on range of P, leaves the range of P invariant, but in general, it will mix these various ground states with each other. Okay, again, this is exactly what happens in the toric code, right? They think of the toric code. These are exactly these X and Z loops that go along the torus. Okay, so now it turns out that there's two loops on the torus. There's there's two non-trivial loops. There's this one, and you can work out the commutation relation of these loops, right? And here it is. Each of them leaves P invariant. So all together, it turns out that this commutation of these two loops is a phase. And you see the phase, it's e to the 2 pi I q over p. Q is an integer, and the little p here, and you see here, this thing is really interesting in particular, when p is not 1, right? So if I have a ground state space degeneracy, right? If I have more than just one ground state in my system, again, as is the case on the toric code, then in fact I get these loops that commute non-trivially. But you see, I refer to the toric code because it's what you know from the toric code. But again, I insist here, I didn't put anything by hand. There's just this U1 charge. There's nothing else, right? And still, I can always construct that kind of unitary operators that act there. Okay, so let me not go into the proof. I think I don't have much time. I want to come to the actual point that once you have these string operators and these loop operators, you actually see that you necessarily have anyons. So instead of looking at loops, I can now look at these operators. Now let me call them still V, but associated to open strings. And so if I start with, you know, they're not loops. So as usual, as we probably all used to, if omega is a ground state and I act upon it with an open loop operator, then this is an excited state, right? Let me call that excited state phi. And you see again, because loop operators are trivial on the ground state space, if I have this and I have another line that goes from this point to this point, but differently, they differ by a closed loop. So really this state depends only on the final end point, but not on the shape of the string. And so it's exactly the kind of things that we're used to. And now we can ask various questions about this state. The first one you can ask is what is the charge associated to the excitation living here at one end of the string operator? How do you do this? Well, you take a big square around that excitation, and you can, you know, you compute the expected charge in that square in the set in this excited state, right? And you compare it to the charge in the ground state, right? So this is the charge of excited state minus the charge in the ground state. You know, you work this out and you get this here, which is exactly what I had before, right? It's exactly, if you in fact the infinitesimal version of the theorem I had before. So you get this and you see that the charge is Q over P. So we started with a U1 charge, so a charge which has, you know, which is an integer. We started with electrons, right? And what do we get here? We see that these collective excitations, these emergent excitations, carry a fractional charge, right? And the fraction, the denominator is given by the ground state degeneracy. That's the first result. That is interesting. The second one is I finally get back to anyons and to the braiding. So if I think that there's this excitation here and I create another one here and then I move it around the first one. So that was my picture. I braid these two particles with each other. So that's I just act with the loop operator V alpha on the excited states that I had before, right? So you see, let me just do this calculation in the final minute I have. So, you know, V alpha is so first let's look from here. So that's the ground state. A loop operator on the ground state, you know, a contractible loop operator is trivial, so I can put it for free. Then I have V gamma omega, which is my phi. So phi is everything to here, right? Then I act upon it with V alpha, the loop operator, and then I add one here, right? So I haven't done much. It's just a complicated way of writing something simple. But what do I see here? I see again that this product of four operators, this commutation between these two V's reappears. And I know that this is just a phase. So this is just a phase when acting on the ground state. So I'm left again with V gamma ground state, which is phi up to this phase, right? So what do I see? I see that, in fact, I get a non-trivial phase when I braid particle alpha around particle gamma, right? And which phase? Again, I know exactly what it is. So I see that these excitations that are created by string operators are indeed abelian anyons with a phase, which is this fractional phase here, Q over P. And again, P is the ground state degeneracy. Okay, so again, you know, these are things that probably most of you are used to. You're used to seeing these equations, except they're usually in specific settings that are partly built with that goal in mind. Well, here I've just shown that this is in fact always the case. As long as you have a gap and a topologically ordered ground state space, then in fact you necessarily have anyons as quasi-particle excitations, and they carry a fractional charge. All right, and I think I will stop here. You know, there's a relation to the fact that the quantum Hall conductance is quantized this is the same fraction, but maybe I will just stop here and open for questions then. Thanks for your attention.
Okay, thank you. Okay, there's a question from David. Just a second.
Yeah, I don't seem to see questions for some reason.
Yeah, so he's going to ask.
Okay.
Hi. Could you say a bit about the case for spin systems? So, like, if everything goes through the exact same, if there's some slight differences in the construction or anything interesting happens?
Fundamentally, everything goes through, but there's one thing where you have to be, where spin systems become interesting is in the assumption that I have a U1 charge. Mm-hmm. So you see, which charge would you like to pick? Well, you take SU2 as your group, and you take one subgroup of it, right? A U1 subgroup of it. So let's say it's the spin in the Z direction. When does this has an integer charge? Well, that's if you have integer spins and not half integer spins. Okay, and so that's, of course, you can make something out of half integer spins. You rescale them to get an integer. You can do that, right? But there are a little subtlety that comes into the game. And in fact, if you apply all of this, you can recover the Lieb-Schultz lattice theorem, which makes a distinction between, well, there's various ways of phrasing it, but it's an impossibility theorem to have a translation invariant, SU2 invariant, unique gapped ground state if you have a half integer spin. Okay, so yes, there are some applications that are typical of spin system, and there usually the interest is precisely between having an even or odd spin, odd integer spin.
Cool, thank you.
I have a question.
Yeah.
So when you define this open string,
right,
does that imply that you would only have like one type of anyon?
Well,
or
you see,
multiples of it.
Here it's a little bit here. If you want, this would be anyons of Zn, right? So two anyon, you can think of two twice the same anyon as one having a double charge. You can do the same, right? Or it's always the same, but
but you only
just
have
like
one generator.
If you want, right? It's just like in the toric code with group, not just Z2 but Zn.
Mm-hmm. But I guess my question was, in the toric code you have both E and M.
No, so with that we don't have this duality here. There's no dual to that type. One. Yeah, absolutely. Yeah. Mm-hmm.
And then another quick question: when maybe I didn't follow this, but do you derive that it becomes that the anyons are abelian, or did you assume that?
No. You see, it comes out of the construction. In fact, you see it. You see it exactly here, right? That's you see, you do this braiding, and what you get out of it, just a phase. Right, so that's what it means to be an abelian anyon. I mean, in the simplest setting, that's all you see. Yeah, absolutely. Of course, you may wonder, well, here I started with a symmetry which was U1, and I get these abelian anyons. So a natural open question is to say, well, start with another group, a non-abelian group, right? Maybe SU2, or maybe a finite but non-abelian group. Can you reconstruct all of this and get non-abelian anyons? We haven't been able to do that so far, but it would be nice. It would be nice to do. Any other questions?
I don't see any at the moment.
Let's see, yeah. It's always weird to not see anyone, but
I guess if there are no more questions, let's thank the speaker.
Okay, thank you. Thank you, everyone.
Thank you.